All right, so we have, so this particular experiment was on common emitter amplifier, and I've given one particular design, not the best of designs, which perhaps you guys had obtained. So the issue, I'm going to raise a couple of issues regarding the design. And the first thing is, you were given a series of specs, right? Voltage gain, input resistance, voltage swing, harmonic distortion, and things like that. And you were supposed to design the amplifier and measure those and ensure that the design meets those specifications. So now the gain value that we gave you and the input resistance and other things that we gave you, you're supposed to measure that in the mid-band frequency range. You know that the amplifier can be operated at lower frequencies and mid-band frequency and higher frequencies, right? So when you make an amplifier in the lab, how do you check whether it's in the mid-band or not? Because you have to show that the gain in mid-band is, let's say, greater than 100. How do you check whether it's in mid-band? Let's say I have an amplifier like this, right? How will I check in the lab? That is it in the mid-band or not? Gain is constant in the mid-band range. So in the lab, what will you do then? So you'll apply a frequency here. You'll apply a sinusoid. You'll look at the output. You have a certain gain. You will change the frequency and see that the gain is constant, right? That's the characteristics of mid-frequency range. Anything simpler? Out of phase. What he's saying is, along with the fact that the gain changes with frequency, we also get a phase change, right? So in mid-band, what is the phase change between here and here? 180 degree, right? So you should, that's easier. I don't even have to change any frequency or anything. All that I have to go and in the lab apply this and look at this output here and see whether they are 180 degree out of phase or not, right? So let's do that here. How do I check in simulation? Well, let's do analysis, dynamic AC, right? Let's do dynamic AC. When I go under dynamic AC, it says at what frequency do you want to calculate? Let's say, 1 kilohertz, right? 1 kilohertz, and it says what do you want as an output? So we want magnitude and phase both. Okay? And so let's do that. All right. Look at the values that it gives you. Let's look at the output here. The first one, what does it give you? What is the first one? Gain, right? So it gives you a gain of 60.292 and it gives you a phase of 116, minus 116. So it's definitely not in the mid-band range, right? It's definitely not in the mid-band range. Now I want this amplifier. So now what I'll have to do is, let's see dynamic AC. Let's go under limit here. Is it in mid-band? Let's put some 10 kilohertz. Let's put 1E4 here. So let's see. At 1E4, it is minus 168. And note that the gain has gone to 136.8. And if I do an analysis of this particular one, I'm expecting a gain of around 144. Okay, this circuit, if I do DC and then AC analysis, I expect a gain of 144. So I've not reached 144, and the reason is obvious that this is still not mid-frequency. It's still away from 180 degree, right? And that's 10 kilohertz. Even at 10 kilohertz is not in mid-frequency. So now I can go to 100 kilohertz and it will go into mid-frequency, but 100 kilohertz becomes a very high frequency, right? So suppose now, let me go back to dynamic limits and let me put it here, 1E3 again. All right, 1E3 again. And at 1E3, I want it to be in the mid-frequency range. What changes should I do? It's not in the mid-frequency. I don't want to disturb gain. I want the gain to remain the same. I don't want to disturb my biasing and all of that. I don't want to do that. But I want at 1 kilohertz for this amplifier to work in the mid-frequency range. How do I bring it in the mid-frequency? Which means I want this phase to get very close to 180. What do I do? As I said, I don't want to disturb biasing, so I'm not going to change 22K and 6.8K because they determine my gain, input resistance, all of that. But at 1K, this is not in mid-frequency range. I would like it to be in mid-frequency range at 1K. What should I do? Coupling capacitors, fine, because 3 dB frequency is lower, 3 dB frequency is 1 by 2 pi RC. So if I can't touch any of these R's because they affect the rest of the circuit, then I should touch the capacitor. Alright, which capacitor should I touch now? C2. Why C2? Huh? 210, okay. Alright, fine, C2. Why C2? Because C2, you see, 3 dB frequency is 1 by 2 pi RC. The resistance that C2 sees is RE in parallel with resistance looking into the emitter. And that resistance is very low. So what he's saying is if you had to change one particular capacitor, maybe go ahead and change C2. Right? So but before that, just suppose I change C3 for a moment. Right? Let me put dynamic AC back again. Limits here. Okay. All right. Yeah. Okay. So we'll focus on, sorry. All right. Anyway, you guys can see. So let me start by changing this one and let's see what effect it has. Let me make it one order higher. 100 mu. No change. Right? Hardly anything. So it doesn't pay. Even 10 times increase, no change. You can see that even here. 100. Hardly anything. There's no point. Well, here, that's what we expect. 100. 166. Right? So immediately, this is the key capacitor here. Now, in my design, there's no point in unnecessarily choosing a very large capacitor. So 10 micro, can I decrease it to 1? You think so? 1? What will 1 do? Well, it does make a difference, so I shouldn't go to 1 here. So 10 is okay. But still I'm 166, I'm not close to 180. Right? So what should I do? Maybe make 200. Let's see what it does. 200, 172. I still have a gap of 8 degrees. I'll have to make it very large, as you can see here. 5, 176. So I have to, it's becoming very large. So I don't want to do that. Let me just take 100 and take an easy way out and increase this to 1E4. So live with a mid band of 1E4, and that's 178.685. The gain is still, as I said, when I theoretically calculated gain, is giving me 144. 144, and how did I theoretically calculate gain? GMRC. GM times RC parallel RL. This is not giving me 144. Giving me 139.7. It's close, but it's not 144. What else could be a problem? Midband is not going to change now. If I go from 178 to another 2 degrees and all that, it's not going to change this. So it's well in reasonably okay in midband. Why is the gain not tallying now? Where is this? Why is it not 144? So in this, for example, if I get rid of exit analysis and what I did was the following. If I do dynamic DC, it gives me this. And then I looked at the current. 3.415 is IC. So I took the exact same value of current, 3.415, calculated GM, and multiplied by RC parallel RL. Right? And both RC and RL are the same. And I did that and I got a value of 144. But in my now simulation, I'm not getting it. Right? I'm not getting this. It's close, but it's not 144. What could be the problem? Is there an approximation involved in GM RC parallel RL? RO, right? So it is GM RC parallel RL, parallel the resistance of this particular path here, R0. How do I check R0 in this transistor? How do I check R0? Or how do I make, let's say, if I make R0 very large, then it should come to the value of GMRC parallel RL. I should get close to 144. How do I make R0 very large? R0 is what? Early voltage divided by ICQ. I don't want to touch biasing because biasing. So I should go and look at the early voltage. So what I do is, let's say I double click this one here and I can edit the model parameters. Let's see where is the early voltage. VAF. VAF is the early voltage here, and that's 100. And to check whether it's really making a difference, let me just make early voltage very high. So let me add artificially high. Let me put 10,000. Okay. All right. Okay, 10,000. Let's look at again. 144. Right. So that was the error. So that early voltage of 100 is introducing a little bit of error. And when I make early voltage very large, then I get the theoretical value that I'm looking for, right? So, okay, let me now, I don't want this artificial value, so let me put it back to 100. Let me put it back to 100. Okay. Fine. So this is giving me then, again, back to the value, is giving me a gain of 139. Right? So we've seen midband, we have seen where gain may deviate from your simple formula, and the other one is suppose I want to, in this case, I want to, for a moment, I'm getting a gain of 140, I want to double it. Now that you've designed the common emitter amplifier, how do I double it? How do I double it? What are the ways of doubling the gain? GM, RC parallel RL, right? So RC parallel RL. Let's focus on the resistors. So resistors, if I double, okay, shall we double this? Both, I can double RC, but RL is usually a load. I'm not allowed to touch it. But in this case, let's double it. Let's put 4.4 and let's put 4.4. So I doubled RC and RL. The gain has fallen to 10. Huh? I changed RC. Why? Does collector current depend on RC? I mean, to the first order, if you look at the circuit, what determines the collector current? See, this R1 and R2, they develop a voltage at this point. This voltage goes and minus 0.7 develops a voltage here. Divided by RE gives me the collector current. RC is not involved in the determination of current. But then why has the gain fallen then? Oh, you're right. If RC and RL have been doubled and gain has still fallen, so something must have happened to the GM part there. Is the transistor, if you simply double this RC and RL, doubling RL doesn't do anything because it's a capacitor. But if you double RC, right, what will it do? It will increase the drop here. And as you increase the drop, what may happen to Q1? Go into saturation. So I think that's what will happen. If we go and look at this and check, can you see whether, when you press this one on, it tells you whether the transistor is in linear region or saturation region. It's saying it's in saturation. I can go back and put 2.2K. And you can see here, it goes back to analysis, alright, analysis, dynamic DC. So now it says linear region, which means it goes into forward active. So it's not so straightforward to double the gain. I can't simply go and RC and RL and simply double them and I'll get the double the gain. The other one you may be thinking is GM RC parallel RL. So maybe I should double GM. And how do I double GM? GM is ICQ by VT. How do I double ICQ? Very simple way of doubling ICQ. If you look at the circuit, what will you do? What determines ICQ? RE, right? If I half RE, then it should double. So let me half RE. Half RE would be how much? 280. Okay, so let's do that. It goes into saturation again. Why did it go in saturation now? Because when I double the current, the drop again across 2.2K increased, and the transistor goes into saturation region again. So again, it's not so trivial that one can simply, there are many other factors involved. I can't simply double the gain, right? Okay, so to double the gain, then I will have to sacrifice something else, right? I have to make sure that the transistor, if I go and look at dynamic DC and I look at the voltages here, you can see here this is 4.487, this is 2.659, and so basically I'll have to increase the drop here, as you're saying. Either you double RC or you double ICQ, you have to increase the drop across this particular resistor. And therefore you have to decrease the drop here. And therefore maybe I have to do something with, all this RE and all that. Instead of 1.9 volt, I have to reduce the drop across RE. And similarly, I'll have to compromise the drop across the transistor. So all these drops I'll have to reduce, which will allow me to increase the drop across RC, and then that will let me increase the gain. Now, are you seeing the drawback of that? If you increase the drop across RC, and let's say you reduce the drop across RE. Right now the drop across RE is 1.9. Suppose I reduce it to 0.5. What is the drawback of that? Drop across RE, I reduce it to 0.5. I redesign and all that, my circuit, the voltage drops and all that. But right now it is 1.9. I make the drop across RE 0.5. And that extra 1.4, then I give it to RC. The drop across RC. And therefore, my gain will increase. It will not double, but it will increase. But why do you need a drop across RE? Why is RE there at all? Why is RE there at all? Huh? Because you want to make the biasing stable. For example, if beta changes and if temperature changes and all that, you want the biasing to be stable. And that's why you put RE. And the voltage drop across RE is a measure of how stable your biasing is going to be. So when I say instead of 1.9, I'm going to make it 0.5, what am I doing? I'm compromising stability of the amplifier. So if I compromise stability of the amplifier, reduce the drop across RE, give that extra voltage now to RC, I'll increase the gain. But that increased gain is coming at the expense of reduced stability. Right? Similarly, if I reduce the drop across Q1, what am I compromising? Why do you need a certain voltage across Q1? To keep it in forward active, right? Now, if I compromise that, my transistor will very quickly go into saturation. So it will limit your voltage swing. So these things are all related together. If you try to increase the gain, you will have to compromise stability, or you'll have to compromise the voltage swing here. So it's not so trivial. And what we were doing was, we were simply doubling RC, and we compromised the drop across the transistor, and it was going into saturation region, and we were not getting any swing at all. Once it goes into saturation, it's virtually no swing, right? And not only that, we didn't get gain also. So, so one has to be aware of that as I try to increase something, what happens? So stability is compromised, swing is compromised, and all of those things are the important aspects of design here. I'll come back to this, but when you make an amplifier, it may happen that my power supply that you see here, 12 volt, my power supply may have a ripple. It's not a clean power supply. Let's say it has a ripple. Now this ripple, that if it is there here, VCC, the ripple is going to go through this and appear at the output. And that's an unwanted signal. So the issue is, how much ripple do I get here? So let's see if we can answer this. So I'm going to take this, I'm assume, so this is input. I'm going to remove the input here now and take this here, right, and add a ripple here, right, add a ripple here. Add a ripple here, and input has been removed. Now the ripple has been added, and now what do I want? I don't want my ripple to appear at the output. Correct? A good amplifier would be that even though you have ripple in the power supply, no ripple actually gets into the output. So the amplifier should sort of reject the power supply ripple. And we have a parameter called power supply rejection ratio. I'll not go into the details, but now that we have put it here, how do I check how much? So now I'm looking for what? I'm looking for gain between this point and this point. And this gain should be as small as possible for a good amplifier. Now, can you predict what will happen? What do you think will be the gain? This ripple is going to go through this, and then what will happen? How is this ripple traveling to the output? Can you see? Can you see the path of the ripple? So the ripple starts from here, sinusoid, goes here. There are two paths as you can see here. It can go down and come here, correct? Or it can go here and come down here at this point. Now at this point would be what now? We're talking about ripple as a sinusoidal ripple. So this point is what? Is connected through a capacitor to ground. So it's like AC ground, right? So will a ripple appear over at the base at all? No. So there's no ripple which will come here and appear towards the base here. So the only path for the ripple is to go through this here. So if there's no voltage in the base, then what will happen now? What kind of a ripple will appear at the output? What do you think? Let me run the simulation and see whether dynamic AC. So we are in midband, and look at that. Look at the output here. So remember what it does is, it assumes that the AC voltage is 1 volt. So it says 1 volt is coming here. And what is happening? Can you see that what is really going on is this 1 volt is coming from here, 1 volt ripple. This path is inactive. 1 volt is coming here. Half the voltage is dropping across RC and half dropping across roughly RL. Look at the value. Sorry. About 482.48 across this, and across 0.48 is across this. Remaining 0.52 is across this. So it acts as basically a voltage divider. You can take and draw a small signal circuit for this one, and you can easily convince yourself when you draw a small signal here that this basically acts like a voltage divider. And basically whatever you apply here, so if you have 100 millivolt ripple, 50 millivolt will roughly appear across the output. That's not very good. It's not really, rejecting it very well. About half of whatever ripple is here appears over here. So that's not very good. But then, where else can a ripple be? Power supply is there. Your ground in your amplifiers and circuits can also get corrupted. Ground may not be a perfect ground. Because note that to this ground, there are a lot of other circuits connected. And the ground is not really a perfect metal. It has a certain resistance. So as the current flows through the ground, the voltages and all that change here. So what if there is a ripple in this? What will happen now? So let's take this out and add a ripple here. And we can do all of this and see what will happen. What do you think will happen now? Where do you think ripple has more effect? Ripple here or ripple here? Ripple here we just saw. Half of it appears here. Now what will happen to this ripple? Let's look at it here. This point is again ground, right? So don't worry about it. This ripple starts here, and this capacitor provides a short. Right? So this ripple, the same ripple value will appear at the emitter. Correct? Everybody sees that? Base is what? When you do small signal? Ground. So what happens across the base emitter junction? You get a very significant voltage. The entire Vs that you see here appears across the base emitter voltage. And whatever appears across the base emitter voltage, gets amplified. That's a normal amplifier. Amplifier was what? You were applying a voltage here, that voltage was appearing across the base emitter junction and was getting amplified. Now the same thing is happening here. If you have a ripple in the ground, this ripple will appear here and effectively appear across the base emitter, because base is effectively AC ground. So let's look at the gain now and see how much appears here. Analysis, dynamic AC, 1E4. Can you see here? 139. So if you really apply any ripple here, it's going to get amplified by the same factor 139 and appear at the output. So your ground is, anything that gets into the ground also gets amplified. It's not just at the input here, but anything in the ground here. So you have to make very good ground in your circuit. Otherwise, any noise in your ground will show up at the output straight. It goes from here, gets amplified and appears over here. Right? So that's again. So if I look at, so the circuit in that sense, any ripple in this power supply gets here, but at least it gets attenuated by half. But any, ripple here, it just gets amplified. So remember, in many circuits, we have dual power supply. We have a power supply, let's say +5 here and a -5 here. So ripple in the negative power supply is going to create a havoc with your circuit. Any ripple here will get amplified and appear over there. Okay, so that in that sense, this circuit is very bad. That any ripple here in this negative power supply, it just creates a huge issue. All right. So let's neglect the ripple part and come back here. Let's go back here. All right. Okay. So what were the other specs? Who remembers the specs of this amplifier? One was voltage gain. Other one was harmonic distortion, right? How do I check harmonic distortion here? How do I check harmonic distortion? We were supposed to get, I think, roughly 0.8 volt peak to 0.8 volt output voltage here. Okay. So if the gain is, let's say, 140 and I'm looking for an output voltage of 1 volt. So how much input voltage should I apply? I should apply a roughly input of 1 volt divided by 140. So 1 volt divided by 140, according to my calculation, would be around 7 millivolt. Okay. So let's apply 7 millivolt here. 7 millivolt here. Okay. All right. 7 millivolt. What analysis should I run now to check whether I'm getting the output voltage or not? Not AC. AC is a small signal analysis. So I should run transient. So run transient analysis. Okay. Let's look at the V output. Let's run it. Okay. So let's see. I get a value of here. Negative is -1. Positive is 0.91. Now positive peak is different from negative peak, and that's an indication of distortion. If I didn't have distortion, it would have been perfect. Same value and same value here. But I'm getting very close to, as you can see here, negative, I'm getting 1 volt swing. How much distortion do I have in my circuit? Well, what you do is you run harmonic distortion. It will tell you how much distortion is there. So you run this one, and you run this, and if you see here, I'm running at 10 kilohertz, making sure it's in mid band. I'm applying an input, is Vs, I'm applying an input of 7 millivolt. And the rest is the frequency range and all that is there here. And I'm looking at total harmonic distortion, THD. Okay, so let's run this. And I get a harmonic distortion of, this is the value here, about 6.2%. 6.2% harmonic distortion is there in this particular amplifier. Now, if I go back and look at what will reduce the harmonic distortion, will harmonic distortion change with Vs amplitude or not? As I apply my input, which is larger and larger, will the harmonic distortion increase? Or is harmonic distortion independent of this input voltage? All right. If you're in doubt, let's put smaller value, 1 millivolt. All right. Let's run. So harmonic distortion, 0.893%. So harmonic distortion increases with the input amplitude. As you increase the input amplitude, what is happening at the output? The output amplitude also increases. So with the swing, the harmonic distortion increases. So, for example, so if you want a larger swing, then I will have to apply a larger input voltage. Let's say if I apply 15 millivolt, if I apply larger input voltage, now let's see what this harmonic distortion is. Well, it's gone to 13%. So that's the price that you have to pay. As you go towards larger and larger swing, your harmonic distortion is also increasing. Okay, in this case, when I apply 15 millivolts, so 7 millivolt was giving us 1 volt output, 15 millivolt will give us about 2 volt output. But then there is significant harmonic distortion. That's the price that you have to pay. Now, what is showing you roughly is showing you how much harmonic distortion? Let's see, 13%. What does the 13% harmonic distortion really look like? Let's go and see that. Let's do a transient analysis and see how bad is 13 millivolt. So let me apply 13 millivolt here. Right, 13 millivolt. Let's look at the output. Analysis, transient, so that you see what is the implication of 13 millivolt here. That's how your sinusoid looks. Now, how bad is the sinusoid? All right, let's look at that. Let's look at the negative peak. Negative peak is, as we said, minus 1.982, right? And positive peak. Can you see here? Positive peak only reaches 1.57 and negative peak reaches minus 1.98. So it's a pretty distorted sinusoid, right? You're expecting close to 2 volt here, and all that you're getting on the positive side is 1.5. And on the negative side, you're getting minus 1.9. Right? So it's a 13% distortion is fairly significant distortion. As you can see here, the sinusoid looks clearly, visibly distorted. Right? So it's not a distortion maybe that you can live with. So you have to keep distortion more manageable to a lesser value. Okay, so that's voltage swing. How do I check what is the input resistance of this amplifier? Small signal input resistance of this amplifier. Small signal means you do AC. And input resistance will, how do we calculate? How do you do that in the lab? You'll put a resistor here. Right? You put a resistor here, you measure the drop across this particular resistor, that will give you the current, and current divided by this voltage will give you the input resistance here. So same thing I'm going to do in the simulation, except that I don't have to put a resistor. Simulation just gives me the current in this by asking what is the current flowing through the capacitor. All right. So let's do that. Let's go AC, and I'm not looking for gain now, and I'm looking for this one here. Voltage divided by current through the capacitor, right? So let's put this here and let's run. So that's the input resistance here. So I'm looking for mid-band. Mid-band is where things are not varying. So input resistance is 0.67K. 0.67, 670 ohms here. So that's the input resistance here. Now, interesting thing, let me bring here. I'm not happy with this input resistance. I want a factor of 10 higher. 10 higher input resistance, 6.7K I want. All right. I'm really ambitious. I want 6.7K. So how do I do that? Input resistance depends on what? Look at the circuit. Input resistance is, this is resistance. Here is R pi. R pi comes in parallel with R1 parallel R2. So I want now 10 times higher input resistance here. So what should I do to R pi? R pi I have to increase. And how do I increase R pi? R pi is Vt by ICQ into beta. So how do I increase ICQ? How do I decrease ICQ by a factor of 10? What's the simple way of decreasing ICQ? Beta I can't change. Alright. So simple way of increasing is increase RE. Right? So alright, suppose I increase RE. Now increasing RE will decrease current, right? And decreasing current means the drops and all that will decrease. So transistor will not go into saturation region. That's not a problem. Do you think my input resistance will increase by a factor of 10? Let's see that. Well, it has increased, but it's increased to 3K. It should have increased to 6.7K. It didn't increase to that. What could be the reason? I increase R pi, I didn't increase R1 and R2. R1 and R2 also come in parallel. So let me increase it all by a factor of 10. Let me make it 220K and let me make it 68K. Alright. Then let's look at it. Right. It is come to 6.8K. It's increased by a factor of 10. So that was easy. Increasing input resistance is at least all that I had to do was increase RE by a factor of 10 and also simultaneously scale R1 and R2. And things have gone up. I've increased by a factor of 10. What did I lose in the process? What do you think I lost in the process? Let's come out here. AC. Input resistance is a factor of 10. Did I lose output resistance? Output resistance is how much of this amplifier? Same 2.2K. RC is the output resistance. So I didn't lose output resistance. I increased gain by a factor of 10. And you know, in design, there are trade-offs. So I must be losing something. What did I lose? What did I lose? Let's run this. Okay. Let's check this gain. 1E4. Can you see now how much? What was the gain earlier? 144 or 139 is to 14.9. I lost gain. I lost gain by a factor of 10. I increased RI by a factor of 10. I lost gain by a factor of 10. Did I lose something else also? Why swing related? More voltage is dropped across? No. RE, see, what I did was I increased this resistor, but then the current also went down, right? So the product remains the same. The drop across RE didn't change. Right? The drop across RE didn't change. The drop across this reduced, and therefore the drop across the transistor actually increased. So why should I lose the swing? Will I get 1 volt swing now? Is it easy to get 1 volt? Remember, at 1 volt swing, how much distortion was I getting? Around 6-7%, right? 1 volt swing. Now, to get 1 volt swing, here now, how much input voltage should I have to apply now? To get 1 volt swing. Remember, what was the gain now? 14. So to get 1 volt swing, the input voltage should be 1 volt divided by 14, which is how much? 1 volt by 14 is like 70 or 80 millivolt. What will happen if I apply 70 or 80 millivolt here? Can I really apply 70, 80 millivolt? Let's see. All right, let's do that. So so I want 1 volt swing, right? So let's do that. Let's put here 70 millivolt, right? 70 millivolt. Okay. Let's run the transient analysis. All right. Any guesses what will happen? It's doing multiple passes to arrive at steady state. All right. So this is what is happening now. 1 volt swing. I can't get 1 volt swing, and that will obviously, that your transistor is linear. If you go back, your transistor is linear when you keep it under small signal condition, and for that the base emitter voltage you have to keep much smaller than VT. VT is 26 millivolt. I have to keep much smaller, and I've applied 70 millivolt. So there's no way I can get 1 volt swing. Now I have to apply something similar. So if I apply, let's say 13 millivolt. 13 millivolt is also higher. So if I apply 7 millivolt, remember we were applying 7 millivolt and getting 1 volt swing here. If I have to apply 7 millivolt, my output will not be distorted now. See, it's not distorted. But how much swing do I get? I lost swing by a factor of 10. Almost like a factor of 10. I lost swing also by a factor of 10. So when you lose the gain by a factor of 10, then you cannot apply very large input, because remember, distortion is related to how large an input you apply. If I have 7 millivolt input, then I get a certain distortion. If I double the input, the distortion also doubles. So if I don't want distortion to increase, I must keep my input the same, 7 millivolt. And if gain is lost, then the output swing is input multiplied by the gain. And so I lose the swing also. Right? So it was very easy to increase the input resistance. We managed to increase it by a factor of 10. We lost gain by a factor of 10. And we lost the swing also. Swing also went by a factor of 10. Right? So now the issue is, I'm willing to compromise gain. Suppose I'm willing to compromise gain, but I don't want to compromise swing. I don't want to compromise swing. That is, so now understand, I want to increase by a factor of 10 the input resistance, okay, which we have done. But gain is okay. If gain has fallen by a factor of 10, it's okay, fine. But I don't want to compromise swing. Because no, you remember, if I don't have enough gain, I can put a stage before that which can build up gain, right? But this one has to give me a swing. My load is connected here, and the load requires a certain swing and certain power. So I have to provide the swing here. So how do I get the swing? In this case, what I wanted to tell you is, this is not the only route for increasing the input resistance. How else can I increase the input resistance? Let me go back here. 560. Let's go back here. 22. How else can I increase the input resistance? Let me ask. Without reducing current. Is there another way of increasing the input resistance without decreasing the current, without increasing this? Because remember, what is input resistance? Input resistance is looking into the base. Base, what do you see? R pi. Why do you see R pi? Because the capacitor here is shorting it. But if I don't have the capacitor, then what will happen? It will be R pi plus 1 plus beta into Re. Right? I can increase the input resistance. Why do we put this capacitor? We put this capacitor to get gain. But suppose I remove this particular capacitor, then I can get high input resistance and I can compromise the gain. Okay, so we don't have time now, but what I wanted to show you was this circuit here. Look at this one. So R1, R1, R2, all these have been scaled by a factor of 10. But that 560 ohms, how much did I have in that one? I had 560. So 560 is still there. But I've added, actually I didn't remove the capacitor from the whole part. I just added a small one here, 60 ohms. The 60 ohms itself getting multiplied by a factor of 100 will give me 6K. So all I need is 60 ohm resistor here gets multiplied by beta and gives me 6K here. And therefore I can get high resistance here. And the 60 ohms is what is now not covered by the capacitor. So the gain will reduce. But then what is very interesting is the 60 ohms that you see here, it provides a negative feedback also. Earlier, the negative feedback was there only in the DC because the capacitor was shorting the. Now negative feedback is there even during the AC. And the negative feedback, one of the effects of negative feedback is it reduces distortion. So in this case, I'll pass this circuit on to you. For those of you who are interested, you can simulate and see that you can get high input resistance. You will compromise gain, but you will get the swing. You can get very good swing here. You can easily get 1 volt swing here. Now, gain is compromised, but you can apply large input here now. You can apply 20 millivolt or 30 millivolt, and still the circuit will work in a linear manner because of the 60 ohm resistor, which provides negative feedback and keeps the distortion low. And thereby you can get the swing part. Gain, you have to live with. Right? Okay, so let's stop here.